Hello class, welcome to chapter 7. We talk about the central limit theorem. Central limit theorem has a shortcut, we call it CLT. Okay. Now CLT is one of the most powerful and useful ideas of all in all of statistics. What we do here is that we take a given population, okay. Now, if we know what the distribution of the population is, it makes life a lot easier, right? If we know what distribution is, it binomial, is it uniform, is it normal? Now, if we have that information, we can use the properties we've seen all along. But if we do not have that information, then we use CLT to kind of overcome that hurdle. So when we don't know much about the population, but if we draw samples, so I'll say you draw a sample, one group, one set, and I'll say sample 2, etc. something, sample n. Now if I draw these samples and if I took the mean of each one of these, mean of sample 1, mean of sample 2, mean of sample n, again you might say, why mean? Well, mean is middle ground for comparison, right? Because it is giving us the average. It tells us, it accounts for all the data values as opposed to other measures of center like median or mode. In median, you really don't account for all the, so even if there are outliers, if values lie outside your normal range of values, it still would not be affected in the sense it's just going to go down to the middle value in median. But if it's mean, it helps us to find the middle ground because it accounts for all the data values. So we have to be cautious about outliers. And so it makes us a little more cautious about how we deal with our data. And of course, it's easy to calculate, so we like our mean. Okay. In fact, there is a CLT for sums as well. We're not going to look at that. We're going to focus only on the CLT for means. So what happens is, if we took all these means, right, for each one of them, and we are saying, well, these samples, to even make this idea meaningful, we want the sample size to be, I'll just say, greater than or equal to 30. That's just a general rule of thumb. The more you have, the better, right? So every sample, right, we're trying to draw, the sample size as a rule of thumb should be at least 30. This is important if you did not know what this population distribution was. If it was unknown, if the distribution was unknown for the population, then we have this condition. If you have the population, if it's given to you that it's, say, normal, then the sample size doesn't matter as much because, because of the population backup. The backing from the population allows you to have even smaller sample size if you know that the population is normal. If it's not normal, go for 30 or more. Okay. So the important fact is that if you took these sample means, right? So when you take mean from a sample, right? We call it x bar, right? If it is from a population, it is mu, the Greek letter. If it's from a sample, it's x bar. Now we have several samples, so I'm going to call it x1 bar. I'm going to call this x2 bar, etc. xn bar, right? So if these were your data values are now the sample means, then what we're saying is these sample means, not x but x bar, will follow normal distribution, and that is no matter what the distribution of the original population is. So that is what CLT assures. CLT assures, the central limit theorem says, if you are drawing your samples from a population whose distribution is unknown, and if you make sure that your sample size is at least 30 for each of those samples, and if you took their means, x1 bar, x2 bar, etc., if you took their means, then the distribution of sample means will tend to follow the normal distribution, despite the fact that we do not know the distribution of the population. And as you can see, that's what I've written here. And we must understand that sampling is done with replacement. Okay, that's again important because then it doesn't alter the sample size, because if you remove them, then you won't be able to generate sample sizes that are large enough in this case large enough would be greater than or equal to 30. So we're going to focus on central limit theorem for means, and as I illustrated before, now this is going to be very helpful for us because we are looking to obtain or draw samples that are large enough and for when we say large enough, we want it to be greater than or equal to 30 if the original distribution is unknown and sample size can be basically any. Okay, so I'll just say any sample size if you have the assurance that the original distribution is normal. So we can kind of see two cases, right? One when it's unknown and when it is normal. So unknown distribution. So from this unknown distribution, if you draw samples of size 30 or more, and if you took their means, so I call them sample means, you collect all their sample means, then we're saying the distribution, so I'll just say sample means x1 bar, x2 bar, etc., xn bar, right? So the distribution of these x bars will be normal with, when we say normal, normal comes with two parameters, mu and sigma, right? So it's going to be normal with mean of all values of x bar, right? That's the mean. And so the notation for that is mu x bar, which is going to be mu itself, which matches with the original distribution. And the standard deviation of all values of x bar, and it's given by sigma x bar. You see the little suffix there, so it tells us which distribution we're talking about. So this sigma x bar is the distribution that's related to this new distribution of all the sample means. So this distribution has a standard deviation which is the same as the standard deviation of the original distribution divided by square root of n. Okay? And the z conversion, right? Because if you're using the z table, the conversion, because we no longer have x, we just have x bars. So your x bars make up the bell-shaped graph. Therefore, the formula for that would be z is always x minus mu over sigma. But instead of x, we now have x bar minus mu, right? That is the mu there, over sigma. Now sigma is now sigma over root n. It has to be adjusted for the new values. So that's your conversion there. And we had the other scenario where if we had, oops, I put the wrong stem. So this was for the unknown distribution. So I'll come back here. And if it is a known distribution, meaning it is known to be normal, then we have no problem, because for unknown distribution we needed samples of size 30 or more. Here it doesn't matter, any sample size is fine. So we draw samples of any size, doesn't matter, and the rest of the things follow the same way. So the new distribution, mean of all x bar values, is mu x bar is mu itself. Standard deviation is sigma x bar equals sigma over root n. I'm just skipping all the extra words. So mean, standard deviation, and z conversion they all remain the same. What has changed is the size n, right? Which we don't see because to us the formula has the n. But we know that we are actually adjusting it for the size n. That's the difference there. Now, if your n is less than or equal to 30 and you do not have, and the distribution is, the original distribution is unknown, then we cannot approximate it to a normal distribution. So we have other methods like non-parametric methods or bootstrapping methods that we will use to overcome that hurdle. Okay. All right. Here is our example. An unknown distribution contains the test scores of a nationwide standardized test. This distribution has a mean of 90 and a standard deviation of 15. A sample with size n equals 35 was randomly drawn from a population. Using the central limit theorem for means, what is the mean and the standard deviation for the sample mean distribution? Okay. Now look for some clues here. We are told it's an unknown distribution. With unknown distribution, we know that we are particular about the sample size being 30 or more. So we just got a sample with size 35, so we are good there. Now this unknown distribution has a mean 90 and standard deviation 15. You know that is possible because in fact we did that when we looked at discrete random variables. We just didn't know what distribution it was. We just looked for some items that we checked to see if we can find the mean and the standard deviation, right? In fact, for continuous random variable, we were able to find the mean and the standard deviation by using the formulas and drawing the table. And in particular, for the uniform distribution, we just use the A and the B. So we come back here and we just make a note. We say what we have here is an unknown distribution. And that distribution has mean to be 90 and sigma, right, standard deviation to be 15. So these are the details given to us. So now we are asked to find the standard deviation and mean for the sample mean distribution. You know, the sample mean distribution is distributed normally, right, as mu x bar and sigma x bar. And we just saw that mu x bar is the same as mu, and sigma x bar will be sigma over root n. So we're just going to use these, the mean and the standard deviation, to help us get the values for the sample mean distribution. So we know that mean is 90, so we have the 90 itself. And for sigma x bar, it's 15 over square root of n. N is 35. Right? So we're going to go ahead and compute this, and we'll get an approximate answer, 2.535. So we found the distribution to be normal because that's coming from CLT. Right? CLT assures this. And we got that to be 90, 2.535. So you got your mean and standard deviation for your sample mean distribution. So I'll say distribution of sample means is normal with mean 90 and standard deviation 2.535. An unknown distribution is created by the average number of grams of gold per million tons of seawater. This distribution has a mean of 1 gram and a standard deviation of 2 grams. A sample with size n equals 200 million tons was randomly drawn from the population. Using the central limit theorem for means, what is the mean and standard deviation for the sample mean distribution? Okay. Again, we have unknown distribution. And it's created by the average number of grams of gold per million tons of seawater. Okay. So this 200 is well above the 30 mark, so that is good, because for an unknown distribution we want to quickly check the sample's size. And the unknown distribution has a mean of 1 gram and a standard deviation of 2 grams. Okay. So I'll just say unknown distribution we know that the sample drawn from it was 200. Well, that's 200 million tons, but for the sake of calculations we keep it as 200. And the mean was given to be 1 gram and the standard deviation is given to be 2 grams. Okay. Now we know by CLT, central limit theorem, because these conditions were met, guarantees that if you took the sample means, that will follow a normal distribution with mu x bar and sigma x bar. Now mu x bar, again by CLT, is the same as the mu, which we got as 1 from the problem, and sigma x bar is sigma over root n. So in our case that is going to be 2 over square root of 200. That approximates to 0.141. Okay. So then we want to now attach the units for these. Okay. So we'll come here and say the distribution of sample means has a mean of 1 gram and standard deviation of 0.141 grams per million tons, because we're divided by the n, right, or square root of n. So we have that, and if you were to show it in symbols, it's going to be as 1 comma 0.141. An unknown population distribution has a mean of 90 and a standard deviation of 15. A sample of size n equals 31 is drawn randomly from the population. What is the probability that the sample mean is in between 85 and 92? So basically they want us to find P of 85 less than x bar less than 92. Highlight the ones we are given. Mean is 90, standard deviation is 15, sample size is 31. So let's enter all those details. Unknown distribution. N is 31, so we're good to go there. It's more than 30. And the mean of this distribution, this unknown distribution, is 90. And the standard deviation is 15. Now, previously they wanted us to find just the mean and the standard deviation for x bar, right? But here they're asking us to find the probability that the sample mean, okay, probability that the sample mean, meaning x bar, not x anymore, is in between 85 and 92. X bar less than 92. That x bar is very important, because without the x bar, we don't have that CLT situation. Okay, if it's just x, then we use the regular normal distribution setup, so we don't have to divide by that root n. So just right here, I'm going to compute the values for the distribution of sample means. So what it says is mu x bar is the same as mu. In our case, we're given mu to be 90. And sigma x bar will be sigma over root n, which is 15 over root 31. We're going to keep it as it is just for convenience, because we can punch those in the calculator when it's time. Okay. So we basically have x bar to follow, normal distribution with 90, 15 over root 31. Okay. Now, if we were to find this probability of x bar between 85 and 92 using the z table, right, what we would do is, again, I'll give you a gist of what we will do. we're going to use the calculator to compute these values. So we now have mu to be, I should say mu x bar, right? Because this is the x bar values here. The scale is x bar. X bar scale, I'll say. Because now you no longer have individual x values, you now have x bar values, the sample mean from one sample mean from the second sample, and so on. So mu x bar is 90 and sigma x bar is 15 over root 31. This is what we have. Now for this, we have to mark 85 and 92 because that's x bar. So 85 is an x bar value. And that's going to be here to the left of it, somewhere here, 85. Now we don't know how close they are. The 85 could be even closer to 90. I'm just marking it, so don't be too picky about where you have to mark, because we're just trying to eyeball that position. And that I'm marking it as 92. So our job is to find this area. What's the probability? Probability means to find the area in a continuous situation. So this is a bell curve, a normal distribution, so it's a continuous density function. So this is what we're trying to find. And we know that with the z table situation, we have to translate this to z conversion, and so the mean here is 0 and sigma is 1. So I'll get the corresponding 85 mark here. I don't know what that is. I'm going to call it Z1. And I'm going to get the corresponding 92 mark here, and I'm going to call it Z2. It will be the same area we're trying to measure. Right? Now recall that this is a Z scale. And we had a conversion, right? So conversion for z scale in terms of x bar would be, I have to come over here and compute it for z1, because z1 is on the left here. z1 is x1 bar, because we have 85 and 92, so x1 bar minus mu over sigma over root n. So that's a calculation with that over root n. That's what makes the change from a regular normal distribution to a CLT situation. So a CLT works only for sample means, right? For samples. And so we just have a sample. We just saw the example about a sample mean. So we have to use the CLT, which involves the sigma over root n. Okay, so that's going to be 85, 1.86. So my Z1 is negative 1.86. Then I come over here to get my Z2. Z2 is 92 minus 90 over 15 over root 31. That comes out to be approximately 0.74. Quickly check if your values are meaningful. The Z1, which is to the left of the mean, should be a negative value, and Z2, which is to the right of the mean, should be positive. So we got those. So you will have to go to your Z table and do probability of 82 less than x bar less than 9, or 85, sorry, 85 less than x bar less than 92 will be the big area minus the small area, because you know that the z scale gives you the cumulative area. So you take probability of, so let's first write the corresponding values here. Negative 1.86 less than z less than 0.74. So that's the conversion from x bar to z. So you can see the conversion. But when you're using the table, you take the probability of z less than 0.74, that value, minus probability of z less than negative 1.86. Because you know that's the bigger area minus the smaller area, so that we get this. So this z less than 0.74 will be this whole thing, right, to the left of 0.74. And for z less than negative 1.86 will be this area to the left of 1.86. So that's what we're trying to do. We're trying to take the blue minus the red so that we'll get the yellow shaded region. Okay. So if we, let's erase the old marks, but this was a binomial table. So let's go to the z table. And so we have the positive z table and the negative z table. So let's come here. Scrolled off way bottom. 0.74. 0.74 will be positive. So 0.7 here and 0.04 here, right? See where they meet. 0.74 is 0.77035. Minus z less than negative 1.86. So we'll go to the negative scores. Negative 1.8 and then a 6 here. So that gives me 0.03. Did I get that right? Yeah. 0.03144. This comes out to be 0.73891. So we're saying the probability of 85 less than x bar, or the sample mean lying between 85 and 92, is 0.3891, or you can say it in percentage, 73.891 percentage. Okay, this is manually, and of course if you're using the calculator, that's going to be a breeze. So you're going to use the normal CDF for that. And we know how to get to it. It's second bars. Distribution. And we go to CDF. So that will be the second one. And in normal CDF, the values you enter would be, so the lower limit, the lower value. So let's go to the graph here. The graph always helps, even if you're not going to do the manual way. Just drawing the first graph, that first bell shape would really help. So if you look at the yellow shaded region, the leftmost end will be the lower value. So the lower value would be 85, and the upper value, so it starts, the shaded region starts at 85 and ends at 92. So I'm going to write the lower value is 85, the upper value is 92, then the mean is 90, the standard deviation is 15 over root 31. You can enter it as it is, you don't have to find it separately. Okay, and then hit enter, and then that gives you 0.73933357. So let me just round it to 7393. And again, because of rounding errors, because the calculator gives you more accurate values, you have those rounding errors giving us a value that's slightly off. That's why when they say use the calculator in a problem, you really want to use the calculator so that we are accurate in that sense. If they say use the table method, then they understand the limitations of the table, so the answer will be acceptable for the table values. Okay. Well, ultimately, this is what we got, and it's really giving us the idea of how to differentiate between a regular normal distribution versus a CLT. So a regular normal distribution would be used if you are just talking about an individual x value, right? Or a range of values, but it's about the x, meaning an individual entry. But if we talk about a sample mean, x bar, then we use CLT. So we're not talking about a sample. So to illustrate this difference, I'm going to bring in the next problem. This is an interesting problem. Let's start off by reading it. The elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds, 27 passengers. Okay. This converts to a mean passenger weight of 148 pounds when the elevator is full. So on an average, if one passenger is 148 pounds, we can have up to 27 passengers and stay within the limit of 4,000 pounds, which is the maximum limit for the elevator. We will assume a worst case scenario in which the elevator is filled with 27 adult males. Okay. Again, the worst case scenario is not because they are adult males. The worst case scenario is that adult males typically weigh more than 148 pounds just because of their body mass and also the height perhaps. And so typically, okay, we can have exceptions where all 27 of them, those adult males, had a mean weight of 148 pounds. But, practically speaking, that's very unlikely. That's the reason why we say the worst case scenario is that all those 27 passengers, which means the elevator is full, are all adult males. And assume that these adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. So on an average right there, they're 189 pounds. Okay, we'll give or take 39 pounds being the standard deviation. A, find the probability that one randomly selected adult male has a weight greater than 148 pounds. And B, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. Let's come to A and B. Let's just discover what the problem is telling us. Well, we see that the problem indicates that the adult males, okay, those 27 adult males, right? That sample has a mean weight of 189 pounds and standard deviation of 39 pounds. And these are normally distributed. Wonderful. So it is no longer an unknown distribution, it is a known distribution. And we are told that it is a normal distribution of adult males. And we are told that our sample contains 27 adult males. Now, typically we want 30 or more if it is an unknown distribution. Because it's known, and particularly its normal distribution, your sample size really doesn't matter. So n equals 27 works just fine here. Otherwise, we would be worried. Okay. So n equals 27 is fine. Mu is given to be 189 pounds and sigma is given to be 39 pounds. We have these things given to us. Now we need to find we need to answer part A. Okay. So we got all the details we have. So for part A, find the probability that one randomly selected adult male has a weight greater than 148 pounds. Remember, this is one individual. That's your key information there. That one randomly selected adult male. So it's an individual. And if it's an individual, CLT does not kick in, right? If it's individual, a regular normal distribution works. So one randomly selected male is an individual. So then our probability that this one individual has a weight greater than 148 pounds can be written as X, not X bar. It's an individual. So X greater than 148 pounds. So we're trying to find P of X greater than 148 pounds. Okay, let's use the calculator. However, we want to draw the graph here. So the mean for this distribution is 189, sigma is 39, and to be greater than 148, we'll fix 148 somewhere on the left of the mean. So that's greater than 148, which would refer to this shaded region to the right. Okay. So you know already that your answer is going to be more than 50% because the right half of your symmetric bell curve is already at 50%. So you are having a little more from the left of the mean as well. So you kind of eyeball your answer. You know that it's going to be, I don't know, 60 or 70 or 80. It just depends on how far away 148 is in that distribution. All right, so we will go ahead and use the normal CDF. Okay. Now what is, so look at your yellow shaded region, and where does it begin? It begins at 148. So your lower value will be 148. What is your upper value? It goes all the way to the rightmost end, which is towards infinity. So you know you want to bring in a bunch of 9s to indicate that. And then mu is 189 and sigma is simply 39. We are not using CLT. Okay, so then let me just make that super clear here. So this is an individual, so no CLT, regular normal distribution. When I say regular normal distribution, we're simply keeping the mu and the sigma as it is. We don't do the sigma over root n. Now go ahead, punch these values in your calculator and see what you get. So we get back 0.853435 and so on, but we like to round it to 4 decimal places. 8534. Okay. Now if you used your table and did it manually, I believe the answer is 0.8531. As I mentioned, it's due to those rounding errors. So what we will come back and conclude is that, where are we? The question was the probability that one randomly selected adult male with a weight greater than 148 pounds is 85.34%. So there's an 85.34% chance that one male adult that you randomly select will have a weight that is more than 148 pounds. It's consistent. It's consistent with the common sense side of it. It's consistent with the graph as well, because we expected something more than 50, and I would give you a range of 60 or 70 or 80, somewhere there. It can't be 90 as such, or it can't be 95, because we didn't cover the entire distribution. But because 148 is kind of far away from 189 in that sense, it seems to account nicely for 85.34%. Okay, that was for part A. What about part B? Part B, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. We have a lot of clues here. First of all, we're given a sample of 27 males. Okay, sample, not an individual. And in part A, that individual had a weight greater than 148 pounds. But here it is that mean weight, because it's a sample, it's a group. You can't just take one individual weight, you have to take the mean of them. So the mean weight of this group of 27 males is greater than 148 pounds. So that information there, right there, tells us that if you use a sample, it triggers CLT. Okay, and the key word is the mean weight. Mean weight would be the sample mean. So when you see the sample mean, sample for which you're finding the probability, then you know that we have to use the CLT. So let's come here and do part B. Now for part B, we are talking about probability of X bar greater than 148 pounds. Okay. So remember, this is mean or sample mean, I'll say. In this case, it was mean weight. And you know that means it triggers CLT. What does that mean? That means your mu will be, mu x bar will be mu, and sigma x bar will be not just ordinary sigma, but sigma over root n. So we have to make find those calculations as well. So our mu will now be the same as, mu x bar will be the same as this mean mu, which is 189. But sigma x bar will be the sigma. Let me take you back here. Sigma was 39 and n is 27 males. So 39 over square root of 27. Again, you don't have to compute this. We're going to enter this in the calculator as it is. Now when you draw the graph for this, yeah, I intentionally drew this graph with making it tall and skinny, the more pointed peak. Now the way we justify this is the mean was the same previously and here, right? The mean was the same. Mean is, in this case it's x bar, mean is 189. So the mean is the same, but the distribution has changed, because if I were to actually figure out what this value is for 39 over square root of 27, that comes out to be 7.5. Okay, so let me take you back here. For this flatter curve here for part A, sigma was 39, meaning the distribution, the standard deviation was higher, meaning the distribution was more spread out. Remember, that's what we learned. If your distribution is spread out, if the standard deviation is higher, your graph will be flatter and wider. But now our sigma is actually, sigma x bar is approximately 7.5. That's coming from 39 over root 29. I'm doing this to illustrate, although I asked you to just leave it as it is. I'm trying to illustrate that 39 there has now become 7.5 for the sample distribution. So this is no longer x values, but it's x bar values, right? So for this, the distribution has lesser standard deviation. There is not much spread. That's the reason why it's going to, look more of a normal distribution. And it's pointy to indicate that it is tall and skinny, where the distribution spread has reduced. So there's more reliability here. Okay. So again, the point I'm trying to make is the graph here should make sense, that it can't be looking the same as the other graph, because there the sigma was larger and here the sigma is smaller. So less spread. So they are all closer and tall and skinny. Alright, so greater than 148. So here again I'm going to mark this at 148 and shade this region to the right of it. Here too I expect higher probability, because the area is going to be larger. Again, I put my 148 pretty close to 189. Maybe it should be a little more spread out. Oops, I missed all of it. And so I'm anticipating it to be larger, just because the variability has reduced. Okay. All right. So I have 148 over here. Now use your normal CDF. So it's the same function, the same thing we've been doing, just that the players have changed. Okay. Now your lower limit, the left end of your shaded region is still 148, and the right end is still extending all the way to positive infinity, so a bunch of 9s. So those things are good. So you already have it in your calculator. And the mean is also the same, 189. Of course, what has changed is your sigma. So in your sigma, you can put 7.5, but I prefer that you enter the value as it is. So it's 39 over square root of 27. Okay. And then hit enter and see what you get. Remember to close your parentheses and all that. 0.9 9. My hunch was right. In fact, even this was, I should have kind of completely shaded the whole curve, because what this is telling us is it's approximately 1, which is 100%. So you can write it like that, because if you rounded it, it doesn't end here. You have a string of 9s actually. So what does this mean? This means that the probability that 27 randomly selected males will have a mean weight of more than 148 is absolutely certain, right? And you can have a few who are 148 pounds, but if you took the average of 27 randomly selected males, remember again, the key word is randomly selected males. So you're not choosing males who are of a certain height only to make this true, meaning you're not going for a certain height or a certain weight for that matter, to say, okay, all these males were below 148, so their mean weight was 148 or less, and therefore, you know, they had the probability of selecting them, you know, would be a different value. But here we're saying randomly selected males, so they can be of all heights and weights, and therefore if you took 27 of them, such random males, and took their mean weight, then it is absolutely certain that that mean weight, their average weight, will be more than 148 pounds. So let's conclude that. The probability of, I need to go back to the problem, so I'll just look it up here. The probability of a sample of 27 randomly selected adult males having a mean weight greater than 148 pounds is basically 100%, okay, or is absolutely certain. Absolutely certain. It's surely going to be the case. That's what this problem kind of proves. Now, I chose this problem to kind of show you how in part A we did regular normal distribution because it was about an individual, and in part B where we used CLT to discuss about a sample, and therefore the sample mean for which we were trying to find the distribution. Okay. A sample of size 48 is drawn from a population with an unknown distribution. That population has a mean of 100 with a standard deviation of 8. What is the probability that the sample mean is between 98 and 101? Okay. So we have a lot of things. We have unknown distribution, sample size is 48, both are good. Mean is 100, standard deviation is 8. And what is the probability that the sample mean, so it's not an individual, it's a sample mean, and you do know that. That triggers CLT. So unknown distribution N is 48, which is good. Mu is 100 and standard deviation is 8. Because we're talking about the sample mean, probability of sample mean between 98 and 101 is written in words, but the way you will write it is sample mean is x bar, isn't it? Sample mean is x bar. If it's between 98 and 101, it should be 98 on the left and 101 on the right. Just putting it like this itself helps you to see how the graph will look, right? So go ahead and get your graph. This is x bar, so I'm expecting a pointier peak than the sigma, right? The sigma is 8, so the original distribution would have more spread out distribution, but this one's going to be narrower. So mu x bar and sigma x bar would be in this distribution. So let's find out what mu x bar is. So mu x bar is the same as mu, which is 100. Sigma x bar is the same as sigma, but with a root n in the bottom. So that's going to change 8 over square root of 48. So that's what we have here. And if it's 100, if 100 is the middle value, then we can have 98 somewhere here and 101 right there. Looks like it's going to be a thin sliver, and you're trying to find this area, the red shaded area. Alright, time for the normal CDF. Your lower limit is where the shading begins. It begins at 98, it ends at 101, and your mean is 100. Standard deviation is 8 over square root of 48. That gives us 0.765127, which is approximately 0.7651. And then you can go ahead and put this together. And that's your answer. Again, see if they want it in the percentage format, and the rounding for the number of places, and present your answer. A sample of GPA's size is 35, and it's drawn randomly from a population with an unknown distribution. The population has a mean of 3.0 and a standard deviation of 0.6. What is the probability that the sample mean is between 3.1 and 3.3? Unknown distribution, sample size is 35, that's good. All the GPA scores, right, that forms the sample, and that sample has 35 scores, so the sample size is 35. Mean is 3, standard deviation is that. For us to find the sample mean lies between 3.1 and 3.3. Sample mean means x bar lying between 3.1 and 3.3, which means we're talking about CLT. Unknown distribution. It's a good idea for you to pause the video and do it on your own. 35, so it's more than 30, that's good. So to get the corresponding mu x bar for CLT, right? Mu x bar will be the same as mu, which is 3.0, and sigma x bar will be sigma over root n, which is 0.6 over square root of 35. And then let's draw the graph. This is for x bar because it's CLT. The mean mu is 3.0 mu x bar, and then the sigma x bar. So we want it between 3.1 and 3.3. So these both are going to be on the right hand side. 3.1 and 3.3. Let's say it's here. So it's this shaded region, right? So look at where it begins and where it ends. So that, and we already have that information kind of pulled from the problem, but we know that this is going to be 3.1, probability of 3.1 less than x bar less than 3.3. Normal CDF 3.1, 3.3, 3.0, 0.6 over root 35. That comes out as 0.1605, 152,151, 0.1605. If they said round to 2 decimal places, that's fine as well. So the way we interpret is this. This is that the probability that the sample mean lies between 3.1 and 3.33 is 16.05%. So then there is a 16.05% chance of a sample of 35, a sample mean of 35 GPA scores will lie between 3.1 and 3.3. High school boys' mile run times are normally distributed with a mean of 6.7 minutes and a standard deviation of 1.2 minutes. Which time separates the highest 20% of the means of the run times in a sampling distribution of sample size 36 from the lowest 80%? This is a different problem type. We are not asked to find the probability between this and this. Instead, we are asked what time separates these two groups, like the highest 20% of the means of the run times in a sampling distribution from the lowest. So at least the clue here is that we are not talking about individuals, we're talking about a sampling distribution of sample size 36, and we're talking about the mean of the run times. So when I draw the graph, because we do have the distribution to be normal with mean 6.7 and 1.2, so let me come to that. Maybe I'll just write that information. So normal distribution. I'll write this before. That's your known distribution, right? So your n is 36, even better. Mu is 6.7 and sigma is 1.2. And because we have to use CLT, because the problem requires us to obtain the time that separates this in a sample size, because we're talking about the mean run times, mu x bar will be the same as mu 6.7. Sigma x bar is sigma over root n, which is 1.2 over root 36. And now we'll draw the graph. This is x bar values, that's your x-axis. Mu x bar, sigma x bar. Okay. That's your mean. The question says, where does, or what time, mean time, basically. So what will be the x bar value? So that separates the lowest 80% from the highest 20%. So it's like this division point. We're asking what is this x bar value which separates the lower 80% because that's the border value, right? The red mark is the border value, that is at the 80th percent, which means values below that will be 80%, right? So this is 80%, and this part above it will be 20%. So what is that value that separates these two? Now we know that in our z tables, even the calculator, all the cumulative values are from left end to the right end. So it doesn't matter if you chose to work on this using the blue region or the yellow region. Ultimately, we want to get that x bar value at that red mark. So what we want to do now is do it in the reverse order of what we've been doing before. Now we are given the area, right? The area is the same as the probability, which is 0.8. And here the area is 0.2. So we're going to use the information on the probability and do the reverse of it. Remember inv norm? So we're going to do the reverse of it. Okay. I'll give a quick run through if you were to do this manually using the z table. So you'll go to the z table and go to the body of the table and look for 0.8. So let me erase these. So 0.8, we've done this one before, right? So 0.8, this seems to be the closest value for 0.8. Find the corresponding z value and then use the conversion, okay, to go from z to x. So we're given z, we need to find x. So go ahead and use this z score. Oh, I forgot it. 0.85. So z is from the left cumulative, right? Z is 0.85. So the conversion would be x bar is, oh, by the way, remember the conversion would slightly change because it was x bar minus mu over sigma over root n, right? So here you're going to plug in z as 0.85. X bar is what you're trying to find. Mu would be 6.7. And sigma over root n is 1.2 over root 36. So you have to basically rearrange this. When you rearrange this, you get x bar equals 6.7 plus 0.85 times 1.2 over root 36. That's the math part there. Right? Now when we had the regular normal distribution, this is under the CLT, but the regular normal distribution allowed us to go ahead and do this as x would be mu plus z sigma, right? This was when it was x, but now when that x is replaced with x bar, it will be mu plus z times sigma over root n. That's what I have here. Okay. Now if you compute the values here, okay, this gives roughly 6.87. Okay, so that will be the x bar value if you're using the table to obtain this. Okay, now if we were to do the calculator version, then you have to use inv-norm, inverse normal. Okay. So again, remember, you have to do the second bar, go down to the third option, just write it here, second bars, inv-norm. Okay, so here it's asking for three things: area, mu, and sigma. So in your inv norm, area would be 0.8 because I am seeing the cumulative area from the left, so I'm using 0.8. Mu will be 6.7, and sigma, enter it carefully as 1.2 divided by square root of 36. And hit enter, and your answer comes out to be 6.868. 832 and so on. So x bar, very clearly, x bar is 6.87. That's approximated. So you see that the answers match. Right? Now to interpret this, we have to say let me take you back to the table, to the graph quickly. 6.87, right? So this x bar, we've just found this to be 6.87. So these are all in minutes, right? Average minutes. So 6.87 minutes. So that is what we need to separate the lower 80% from the upper 20% of those runners, right? The high school mile runs. So go back to your original question, and then say, so we can simply say, because we were trying to look for the time that separates the lower 80 from the upper, from the top 20%, right? So we can just say the top 20% of running times exceed 6.87 minutes. That makes sense, right? Because if you cross that 6.87 mark, then you are in the top 20%. So that is what exceeds. So you should exceed that 6.87 to be in the yellow region. That's what this means. So you can do your own interpretation, but if you had your question that requires you to interpret in a certain way, you can definitely use this to use as a separating value. Alright class, so I hope you enjoyed this lecture. Again, a quick recap. For CLT, remember central limit theorem states that if you draw samples from a population, samples that are large enough, greater than or equal to 30, even if it's drawn from an unknown population, if you took the sample means of each of these samples and you formed a distribution of the sample means, then that distribution will follow a normal distribution with slight adjustment to the mean and the standard deviation. The mean will remain the same, but the standard deviation will now be sigma over root n. And so when we talk about individual probability of an individual selection, then we use the normal distribution techniques that we regularly use. If we are talking about the probability of a sample mean, so mean of that group, the sample, then we have to remember to use CLT, where your sigma is replaced by sigma over root n. Okay, and so with that we finish off with chapter 7. I will see you in the next video where we will explore chapter 8. Thank you, class.